Hi and welcome back. So we're moving on now to looking at energy transformations. We've sort of gotten a lot of the background of fossil fuels and biofuels and what it means for a fuel in terms of what we're talking about in chemistry. So now we're going to start breaking that down a little bit more into our environmental impacts, energy transformations, and start to look at some of that terminology we need to bring into those questions. So you may remember from, or hopefully you remember from your earlier studies, the idea of the law of conservation of energy. This being that energy is conserved, it is never created or destroyed, that it can only be transformed from one form to another. Okay, so this is key in this. So you're talking about the idea that fuels are burnt in order to produce energy, that a fuel is a substance that stores energy in its bonds in some way. So with this in mind, we need to remember that when we do see substances undergoing these energy transformations, okay, energy isn't created or destroyed, but it can be lost as unwanted energy, usually heat. So when we have friction, we get heat that will take away some of the kinetic energy and things like that. So when we're talking about these energy losses, about 25% of the chemical energy in petroleum is converted into mechanical energy to drive our cars when we use them inside our internal combustion engines. But the remaining 75% is converted into unwanted heat energy. This is why we have radiators in cars, and we need to use oil to lubricate the engine parts. We get so much heat from these engines, and that heat is essentially being wasted. It's not the type of energy that we were after in order to power the vehicle. In the body, chemical energy in food is converted into energy for growth and repair of tissues, mechanical energy, and thermal energy. So we have all these different types of energy and how it can be transformed from one to another. Okay, we've talked about nuclear energy and how it provides a high energy density, radiant energy from the sun. So the sun is actually powered by nuclear energy. That radiant energy will then be used in photosynthesis for the growing of plants. Okay, and then from that we eat the plants and release the energy into our bodies, allowing kinetic energy. That kinetic motion, if put into a motor, can give us electrical energy and that kind of thing. So it is important for us to know the different types of energy and their transformations when we talk about energy production in society. All substances that we're looking at, particularly fuels, contain chemical energy. Okay, so this is chemical potential energy. The amount of energy contained within a substance is its energy content. Okay, so fuels are substances with a high energy content. They have that high chemical potential energy that can be readily transformed into different forms of energy. Okay, so we can access this energy easily, and they have a high amount of energy relative to that substance. Okay, so if we look at this, we see energy content of liquid fuels, okay, hydrogen, methanol, natural gas, which is under pressure and turned into a liquid, ethanol, gasoline, and diesel. So these are our fossil fuel-based petroleum diesels. Ethanol, which could be derived from bioethanol, we can see has about half the energy of these. So this is something to keep in mind when you weigh up the potential benefits or drawbacks of fuels. So as we mentioned with the internal combustion engine, which is incredibly inefficient at 25% efficiency, our coal-fired power stations, which we use to generate electricity, involve several energy transformations. With each of these energy transformations, we will have unwanted energy loss, so energy being lost to heat or various other things. Okay, it won't be completely into the transformation that we're after. This means that our power stations, when running a modern power station running at high efficiency, is only going to be about 30 to 40% efficient. So the energy we get from burning the coal, only about 30 to 40% of that energy ends up being converted into electrical energy for our electrical grid. So, as we talk about energy in our society, it is incredibly important for us to maximize the efficiency of these conversions. This allows us to reduce costs, both financial and environmental. If we can get more of the energy from burning these fossil fuels converted into the energy output that we're after by increasing efficiency, then that means we have to burn less for the same amount of energy and therefore reduce emissions. Okay, so when we talk about energy efficiency, and this is something you should have a definition for, but it is given as the percentage of the energy from a source that is converted to useful energy. This is the desired energy. So if we're looking to produce electricity, we're talking about the percentage that is converted into electricity. So the chemical energy of fuels is typically released through combustion reactions, and then we utilize that to power different engines, generators, and so forth. Okay, bit of coal-fired power station breakdowns. Page 12 of your textbook is where this diagram comes from and goes through it in detail. Okay, what we're looking at is the energy from combustion of coal is about 32 kilojoules per gram. Okay, we're only going to get 30 to 40% of that converted to electricity. And then, as we've discussed, brown coal will have a lower efficiency because of its higher amount of water. So we lose some of this energy into evaporating the water. Remember, and water has a high specific heat capacity and a high latent heat. So in order to vaporize that water and get it out of the coal so it can burn effectively, we first have to use up some of that energy to drive the water out. So the majority of power stations around the world are coal-fired power stations. This means we take a large amount of coal, of which we have chemical potential energy locked away in the coal. This is burnt. That heat energy is used to boil a large amount of water. Okay, so we have chemical potential energy in coal being released as thermal energy of the burning coal, which is then absorbed by the water. So, and we have thermal energy of the steam. Okay, so this is, now we have the heat from the coal going in and producing heat in the water, producing steam. That steam rises out of the boiler, passes through a tube, opens out and turns a turbine. So we have the thermal energy of the steam being converted into mechanical energy of the turbine. That turbine drives the generator, which generates electricity. Okay, so here we have the mechanical energy of the turbine being converted into the electrical energy from the generator. The water is then collected, condensed, and pumped back through the system or out into a cooling tower. Okay, so we have multiple steps of energy transformation. At each one of these transformations, we are going to be losing energy as heat to the surroundings or drops in temperatures due to expansion, these kinds of things. But at each one of these steps, we will lose energy. Turning of the turbine into mechanical energy will also lose some to friction and things like that. Okay, so our power stations run at only about 30 to 40% efficiency. You should be able to list each of the transformations for this. So chemical potential energy into thermal from coal, okay, into thermal steam, okay, which then goes to mechanical in the generator, and then out to electrical. Okay, so again, just make note of these simple transformations, remembering that at each point where we go from one type of energy to the other, we will see a loss of energy. The other thing to consider with this is also the effect of, will we have complete or incomplete combustion? Okay, because if we don't have complete combustion, then we won't be getting the full amount of energy being released from our fuel. So this is our full step-by-step. Coal, chemical energy stored in the chemical bonds of the coal. thermal energy released on combustion. The thermal energy is absorbed by the water and is released from the steam. Steam to the turbine, so the thermal energy is absorbed by the water, and then the movement of the steam through the system turns the turbines. Turbines then generate the electrical energy. Okay. So to give you an idea of what the questions would look like for this, here is a simple question here. We can see a little bit of background. So most of the electricity produced in Victoria is made by burning brown coal in coal-fired power stations. Outline the sequence of energy transformations that occur from the time the coal is heated to the production of electricity in the power grid. Okay, so this is from releasing the chemical potential energy of the coal through to electricity, which we just went through. Which transformation is the least efficient? Have a think about this. Which one do you think might we be losing the majority of our energy? Then name 2 renewable sources of energy, listing an advantage and a disadvantage of each. I want you to pause the video, have a go at answering these questions, and then come back to have a look at our solutions. Okay, so hopefully you've had a think about this. Outline the sequence of energy transformations that occur from the coal is heated to the production of electricity. So we're going to have our chemical potential energy to thermal from the coal. This goes to thermal steam, as we said before. Then mechanical in the generator through to electrical. So which transformation is the least efficient? If we think about these transformations, we know we can lose a lot of heat energy, but if this is nice and insulated, which it usually is, okay, we will transfer a large amount of the heat through both of these systems here because they'll be isolated. This one here, where we are taking steam in order to move, I mean, these turbines are massive, so we need to generate enough pressure through steam to turn this one here. That is going to be our least efficient. Okay, so this would be the from mechanical, thermal to mechanical would be our least efficient step here. Okay, so if we name 2 renewable resources of energy, listing an advantage and disadvantage of each, we could consider solar power. Okay, an advantage being that it is free and non-polluting. Okay, solar panels aren't free, obviously, but the energy from the sun itself is. A disadvantage being that access to sunlight hours, so on cloudy days or things like that, you reduce the power. You could look at wind turbines. You could also consider some of the ones that we've talked about in terms of biofuels and things like that. Again, we've talked about a number of those disadvantages. You could also look at the fact that it needs to be stored in batteries, environmental impact of batteries, those kinds of things. Same goes for wind. The source of the wind or where the turbines are may be a long distance from where the power is needed, those kinds of things. So a gas-powered turbine, we're going to go through this pretty quickly. It runs much the same way as a power plant, except this time we're going to have gas providing we're going to have fuel that is burnt. We've got air coming in and exhaust coming out. The fuel is natural gas typically. Okay, it is burnt in a combustion reaction of methane gas, giving out about 890 kilojoules per mole. We see here we've got a per mole amount because we are talking about primarily methane. Okay, this drives the turbine of the generator producing electricity. So here we just have chemical potential energy and then mechanical energy through into the generator and to electrical energy. The advantages of this over coal output the output can be controlled at short notice, so we can power up and power down gas generators a lot faster than we can a coal-fired power plant. Okay, and then with this, we're using coal seam gas as a more common source of fuel and gas power stations. Very topical at the moment because with the Australian government looking at more gas-powered power stations in the future. Biogas can be used in a similar way. So this is the same as for methane combustion in natural gas generators, but we're going to be using biogas released from biogas fermentation tanks. So we've talked about this in terms of the fermentation of organic matter under anaerobic conditions, producing methane gas. So these large fermentation tanks, which are basically organic matter, manure, things like that, the gas is tapped off, passed into a generator to generate electrical energy. The heat exchanger can be used to heat the farmhouse and greenhouses, and then you can use the solid sludge here as a natural fertilizer. So this, by using all the possible waste from farming to then use in energy generation and heating and things like that, is quite a sustainable approach by using wastes from other processes in order to generate energy. Transportation fuels, we've talked about this in terms of petroleum. This is a mixture of different hydrocarbons obtained from fractional distillation, main one being octane that we use for transportation fuels. So 1 mole of octane produces 5,450 kilojoules, okay, and then this would be kilojoules per mole. Okay, the efficiency of car engines is about 25% though, so we're going to lose 3/4 of this energy, 70%, to heat and general friction and various other things in our engine. So only about 30% actually gets converted into kinetic energy of moving our cars. So the internal combustion engine is very inefficient. So the last ones we've got is LPG and bioethanol. These can be used in cars much like petroleum, okay? So they generally, LPG needs a conversion unit. You may have one in your family car. Okay, the main component of this is propane. Okay, I want you to, in your notes, write the complete combustion of propane, remembering this is prop, so 3 carbons, so C3. Ane, A-N-E, makes it an alkane, so it's going to be CnH2n plus 2, so that's going to be CH8, okay, is going to be your propane fuel, and then we're going to combust that with oxygen, producing CO2 and H2O. Now it just needs to be balanced. And don't forget states. Okay, so LPG tends to be cheaper, but you do need a large tank in order to get the same amount of distance out of the car, because you're not going to be getting as much energy from the LPG as you will from petrodiesel. Bioethanol, again, ethanol generally not used pure in car engines, okay, but put in 10% or blended with petrol to make our fossil fuels go further. Okay, so to diminish that, the bioethanol will reduce the sulfur dioxide and nitrogen oxide outputs of that fuel because it will be pure ethanol. So we've got the CH3CH2OH. There is no sulfur or nitrogen in this, so it will reduce those toxic emissions from our combustion engines. Okay, another long one, I'm sorry, but this is a comparison of the energy content of fuels. You also have some energy data in your data booklet. If we have a look here, energy content is given in kilojoules per gram. Our energy density is per litre of fuel. Okay, so it's important to remember here, energy content, kilojoules per gram, energy density, looking at kilojoules per litre. Okay, so if we look here, 55.6 kilojoules per gram, 23,500 kilojoules per litre for liquefied methane. So we can see methane has the lowest energy density, ethanol has our lowest energy density down here, whereas our fossil fuels certainly have much higher energy densities, the octane having our highest at 33,400, and this is the main component of things like aircraft fuels and things like that. Okay, so that's it for this one. Just make a note of these energy densities and maybe a list of the smallest through to the highest. Again, have a look in your data booklet for the energies and what page they are on. Make a note of that, and I'll see you in class.